Hello, friends. Now we're going to talk about vector valued functions and motion in space. Specifically, we're going to talk about curves in space, such as this blue curve, and their tangents. So we want to go back and consider parametric curves. And I can write three parametric curves. X equals f of t, y equals g of t, and z equals h of t. In all three of these, t is on some interval I. So these represent the particle's coordinates as it moves through space over time on some time interval I. So specifically, these are describing a path in space traced in a specific direction, or rather orientation, as time increases, so over time. So instead of thinking about this as x, y, and z, we're going to consider this ordered pair at the point as f of t, g of t, and h of t, three functions of time for each coordinate, still on that same interval. So this set of points, which is organized using these parametric functions, they make up the curve in space, which represents the particle's path. So we can use these three parametric equations to represent a vector r. So this vector r of t can be also represented as the vector from O to P, or we could say f of t, g of t, h of t. And then using our IJK notation, we could also write this as some function f of t being a coefficient of the position vector I plus g of t times the position times the vector j plus h of t times the vector k. So f of t, g of t, and h of t, these represent the component functions. So let's talk a little bit more about what this r vector represents. So r of t, this vector r being a function of t, I don't need equals, is an example of what we call a vector valued function, or VVF, vector valued function. So r of t is a vector value function at any given time value, t. And the initial point's always going to be at the origin, and we'll have a terminal point, some point on that curve determined by those three parametric components. And whenever we're talking about functions, we have a general domain and range. And we always have to have a domain and range specified for every function we're dealing with. So our domain is going to be all real numbers, and our range is going to be a set of vectors. Okay, I turned that A into an O. So the domain will be, all real numbers, and then our range is this set of output vectors that tell us where this particle in space, they give us clues about its position, direction, orientation, etc. at a specific time t. So here are some examples. We have three different examples of different types of vector valued functions you might see. So here we can see three different space curves, which are all defined by the position vector r of t. So we have some r, And then there is a I, J, and K component that all have a parametric function in front of them. So I think the best thing for us to do is to start by graphing a vector valued function in our R3, in R3 space. So here we're given vector value function R of t. R of t is equal to 4 cosine t times I plus 4 sine t times j plus t times k. And of course, we could think about this in our component form, just reiterating that these two notations mean the same thing. So we have a x and a y and a z component here. So the same way we graphed parametric equations back in trig, where you likely learned about this, is we make a table of values. And we have a t value, x, y, and z. And in this specific equation, it is not specified any bounds on our t values. So we're just going to look at t from 0 all the way to 2 pi. So I'm going to count on my quadrantal angles. We've got 0, pi over 2, pi, 3 pi over 2, and 2 pi. So now, to complete my table, I'm going to look at these t values in each of my components. So my x component is 4 cosine tx, and at this, I assume at this point you can plug these numbers in and get some outputs. So I'm just going to write down what I have on my paper here. I've got 4, 0, -4, 0, and 4. Doing the same thing, plugging t into my y, so I'm doing 4 times the sine of all these different t values. I get 0, 4, 0, -4, and 0. And then for my z component, z is equal to whatever t is, so I have 0, pi over 2, pi, 3 pi over 2, and 2 pi. All right, so let's go back and think about what we learned about some of our parametric equations or polar equations even in our trig class. But what do 4 cosine t and 4 sine t represent for that x and y? And they represent a circle of radius 4. So if we think about what our graph is going to look like in the x, y plane. So here's y, z, and x. So we have a circle of radius 4. So I'm just going to mark out 4 on both sides. I'm going to draw my circle here. And I'll assume that would be -4 on my x-axis and +4 on my y-axis. So I'm going to use kind of a cylinder to help me think about this. This is kind of like an invisible cylinder, but essentially what we're going to be doing is we're going to be traveling around this circular cylinder of radius 4, but we're going to be moving up as we do so. So here is my circular cylinder. I don't like the way that top of that circle looks. This is my best geometric drawing I can do. Okay, so this cylinder is just a frame for what we are graphing. And of course, all my points are going to be on the perimeter of this cylinder, on the outside, or the circumference, I should say. Right, so we're traveling out 4 in either direction here. So my first point in my xy plane, that's going to be this circle on the base, is at x equals 4, y equals 0. So here's my first point. Now, the z is 0, which means I have not traveled vertically. But as we continue around this circle, you'll notice those z values are increasing. And I'm actually going to come over here on my axis and count up to 7. 1, 2, 3, 4, 5, 6, 7. Okay. So then we are going to plot 0, 4, pi over 2. So I'm going to plot in my xy plane on the circle the point x equals 0, y equals 4. But I'm traveling up. I'm traveling up to approximately pi over 2. Pi over 2 is roughly, we'll say, 1.7. So see how I've kind of traveled horizontally over here from 1.7? So there's my second point in space. So my third point in space, -4, 0, pi. So that's going to go back on my x-axis, and we're going to go up pi. Pi is approximately 3.14. So we're going to be up a little bit over 3. So again, as you think about plotting this, I'm going to go back 4. That's on the edge of this circle. And then I'm going to travel up 3.14. So if I look at this, I've got 1, 2, 3.14. Sometimes it helps if you think about drawing that rectangle in perspective. So this point would be roughly about here. So my next point, 0, -4, 3/2. 0, -4 is out this way. And then we're going to go up 3 pi over 2. 3 pi over 2 is roughly 4.8, I think is what I have written on my paper. Somewhere between 3 and 6.28. So anyhow, I'm going to go over to this point, 0, -4, and then I'm going to go up on that outside, somewhere between 4 and 5. So we've got 1, 2, 3, 4, 5, about right here out in perspective. And then my last point coming all the way around, we're at 4, 0, and then we have 2 pi. So 2 pi is approximately 6.2. So 4, 0, and then traveling up here on this axis, 1, 2, 3, 4, 5, 6, we're going to come out. And again, it will help you if you go from 6.12 to travel out in perspective and to try and make this rectangle. So this puts me, it would actually kind of look like about right there. So what's going on is we have this coil that is wrapping around this cylinder. And I've only graphed points from 0 to 2 pi, but I can obviously, since there's no restriction on my t, I can add more t values, which would keep this helix continuing to grow or expand vertically, and then it would also could go down below the xy plane. So that is kind of how we go about graphing a helix. And of course, most of what you're going to be doing is on the computer with this. This would be something that we would do in a lab setting where we would graph these and we would maybe look at them more on the computer. So let me just pull in a couple of different helixes, or in plural, we say helices with a C. So here are some different helices. So the word I'm using there, the plural for helix, we use this C, helices. And so you notice a very similar patterning for all of 3 of these, for A, B, and C. Cosine and the sine have the same arguments and the same coefficients. And then we have a linear parametric component on K. So I hope that helps you kind of understand what these vector valued functions look like and what we're doing. So in the following video, we're going to talk about the limits and continuity of vector valued functions. And we're going to start to get a little bit more into the calculus aspect of this.